Good morning, my dear students. I hope all of you are okay in this situation, and the remaining portions I will share in recorded videos, and notes in PDF form will be shared in your group. I request you to go through the material after the recorded class gets over, and any doubts if you have in any part of the notes given to you, you are most welcome to clarify. So we have completed Huygens wave theory. That is the first chapter in wave optics. And then we are discussing interference of light. In the regular classes, I have covered up to Young's double slit experiment, experimental setup, theory of the experiment, and lastly, fringe width expression. Derivation is not there for the exam. You just know the expression for the fringe width in Young's double slit experiment. However, I am going through the derivation steps in brief for you to recall what you have studied in the earlier classes. So in this figure, first look at the heading, expression for fringe width in YDS experiment, that is Young's double slit experiment. So S1 and S2, the double slits, acts as two coherent sources. Let D be the distance of separation between S1 and S2. Lambda be the wavelength of monochromatic light used in the experiment. Usually it is sodium vapor lamp. Wavelength lambda will be 5893 angstrom units. And here capital D is the distance of the screen from the plane of the double slits. Look at the figure. O is the midpoint on the screen, and consider some arbitrary point R at a distance x from the midpoint O. Then draw S1P perpendicular to the screen, S2P, S2Q perpendicular to the screen. Let theta be the angle of interference or angle of observation at point R. Now draw S1C perpendicular to S2R. So here S1R is the distance traveled by the first light wave in reaching point R on the screen. Similarly, S2R is the distance traveled by the second light wave emitted by the second source S2 in reaching at point R. So from the figure it is clear that S2R is greater than S1R. So this difference in distance traveled by the two light waves in arriving at point R, we call it as path difference. So in the figure, S2C is equal to delta, denotes path difference between the two light waves when they arrive at point R. So therefore, from this right angle triangle, S1, S2C, remember it is a right angle triangle, sin theta is opposite by hypotenuse, that is delta by D is sin theta. Therefore, delta will be equal to D sin theta. That's the path difference. In the figure, S to C is equal to delta, that is D sin theta. And if delta is equal to n lambda, that is a condition for maxima, which we have discussed in the theory of Young's double slit experiment. And if delta, path difference delta is odd multiples of lambda by 2, it may be 2n minus 1 or 2n plus 1 into lambda by 2, where n is an integer, 0, 1, 2, 3, 4, etc. is a positive integer, and is a condition for dark fringes, which we call it as minima. Now come to the geometry of this Young's double slit experiment. So from the figure, from triangle S1PR, look at the figure, S1PR, it's a right angle triangle. S1R whole square is equal to D square plus x minus D by 2 whole square. From Pythagoras theorem, I am writing this. S1R will be equal, S1R square will be equal to S1P whole square plus PR whole square. S1P is D, therefore it is D square plus distance PR will be X minus D whole square. That is equation 1. Similarly, we can write from the other triangle, right angle triangle, S2R cube. S2R cube. We can write S2R square will be equal to D square plus X plus D by 2 whole square. So now from equations 1 and 2, we can write S2 R square minus S2 S1 R square will be equal to 2xd. You simplify this, you will get 2xd. So now use the formula a square minus b square, which is a minus b into a plus b. We can write this step. So therefore, in the figure, S2R minus S1R is delta path difference, and S2R will be equal to capital D because theta is very small. In that case, we can write S2R nearly equal to capital D. Similarly, S1R is also nearly equal to capital D. With that approximation, we can write 2 delta D is equal to 2xd. Therefore, x is equal to d by d into delta. That is equation 4. And case 1, for nth bright fringe, we can write xn is equal to d by d. Put delta is equal to n lambda in this equation. So we'll get d by d into n lambda. Similarly, for n plus 1th bright fringe, we can write xn plus 1 as d by d into n plus 1 into lambda. That means in place of n, you just write n plus 1. So now xn plus 1 minus xn. If you take the difference between two consecutive dark fringes, you will get the width of a dark fringe. So if you substitute for xn and xn plus 1, on simplifying, we get beta dark is equal to lambda d by small d. Similarly, case 2, for nth dark fringe, you put delta is equal to 2n minus 1 into lambda by 2. You will get this. For the next fringe, n plus 1th dark fringe, in place of n, you write n plus 1. It's not n minus 1, n plus 1. Put n plus 1. If you take the difference, you will get the same value lambda d by d even for bright fringe. It means distance between two consecutive dark fringes is a bright fringe. Even bright fringe is of same width lambda d by small d. So thus the conclusion is whether it is dark fringe or bright fringe, fringe width beta is a constant equal to lambda d by small d, where lambda is the wavelength of light, monochromatic light used in the experiment. Capital D is the distance of the screen from the plane of the double slit, and D is the distance of separation between the two slits in the Young's double slit experiment. So this is a formula, no derivation, just remember the formula. Now let us go to the next heading, interference of light by division of wavefront. Just like in Young's double slit experiment, the wavefront is divided by the two slits S1 and S2. Similarly, one more device using which we can study the interference of light by the division of wavefront is a Fresnel biprism. Fresnel biprism. It is an optical device used to obtain two coherent sources using a single source by refraction phenomenon. It consists of two acute angled thin prisms with their bases in contact. It is prepared by grinding an optically thin pure glass plate slightly on the two sides so that each angle of the prism is just half a degree or 30 minutes. The obtuse angle of the prism is about 179 degree and the other two acute angles are 30 minutes each, that means half degree each. So this is how division of wavefront we can study in case of biprism. So figure A shows how a glass plate, it is cut into this portion, not the shaded part, the remaining triangular portion. It is cut from a glass plate which serves as biprism. This is a perspective view of biprism. This angle will be about 179 degree. This angle will be half degree. This angle will be half degree. This is a what is called three-dimensional perspective view of biprism. This is how the glass plate is cut and made as biprism. So here the angle of the prism is just half a degree, and this third figure shows the principal section of a biprism. You can see how the two thin prisms are joined face to face such that the angle 90 degree, they are touching each other. Therefore, angle theta between the two surfaces is about 179 degree, and angle alpha at this end or at the opposite end alpha will be about half a degree or 30 minutes. This is how biprism is prepared. Now this diagram explains how the biprism gives rise to two coherent sources to study interference by the division of wavefront. Look at the figure. So S is an arrow slit illuminated by a monochromatic source of light. It acts as a primary source, and rays of light, they are rendered parallel after refraction through the biprism, and these refracted rays, they gives rise to two images, virtual images S1 and S2 in the same plane as the original slit S. So thus S gives rise to two virtual images S1 and S2, which acts as two virtual coherent sources. Let D be the separation between the two virtual images S1 and S2, and all these angles are marked here. Theta is the angle, and here O is the midpoint on the screen. S1A and S2B are drawn perpendicular to the screen, and here distance of the biprism from the slit S is A, and distance of the screen from the biprism is distance B. A plus B is equal to capital D. Capital D is distance of the screen from the plane of the slit. And T denotes the telescope which is focused onto the screen to see the interference fringes. And here the fringes obtained on the screen is just similar to Young's double slit experiment. That means you will see straight and parallel fringes consisting of alternate dark and bright fringes having equal width. They are formed one after the other, bright, dark, like that. You will see infinite number of fringes on the screen, and all fringes are of same width. And here from the figure we can write, if we consider this triangle S1 SE, this point is E, or S2 SE, from this right angle triangle we can write tan theta as d by 2 by A. So tan theta is d by 2A. This we are going to use in the derivation. So now let us go to the next mathematical part. And in the first figure, we have shown the biprism and other experimental arrangements. So in this figure, to arrive at the theory of fringes in biprism, I am just representing the original source S, S1, S2, two images, virtual images produced by the refraction through biprism, acts as coherent sources. D is separation between them. Capital D is distance of the screen from the plane of the slits, that is plane of the two virtual sources. We are not showing the biprism in this figure. So this is angle theta. Even this angle will be theta. Draw S2G perpendicular to S2P. Join S1P. Join SNP. S2P. Now delta, that is S2G is equal to delta, is a path difference between the light waves arriving from the two virtual sources S1 and S2 at point P. So therefore from the figure we can write delta is S2P minus S1P, which is equal to S2G. From triangle S1 S2G, you should look at the diagram. S1, S2, G. From the right angle triangle, we can write delta as d sine theta. Since theta is small, delta we can write it as d into theta. That is equation 1. And from figure, that is from triangle SOP, look at the figure. SOP, it is a right angle triangle. From SOP, we can write tan theta as x by capital D. Tan theta is x by d. Since theta is small, tan theta can be approximated as theta. Therefore, theta is x by d. That is equation 2. And from equations 1 and 2, equation 1, we can write theta as delta by d. Equate the two. X by d is equal to delta by d. Therefore, delta is x by d into small d. That is equation 3. Let alpha be the refracting angle of the prism. Biprism, which is half degree. The distance between the source and the screen, that is eyepiece. Capital D is A plus B, where A is distance between the source and the biprism, and B distance between the biprism and the screen, that is eyepiece. Now let us work out the conditions for constructive interference. So in the notes, remember CI denotes constructive interference. Case 1, condition for constructive interference. We know that x is equal to capital D by small d into delta. I am just taking from the previous step. Delta is equal to x by d into small d. From that I am writing x is equal to capital D by small d into delta. Put delta is equal to n lambda. Therefore, distance of the nth bright fringe on the screen from the midpoint is given by x lambda d by small d. Similarly, x minus 1 is n minus 1 into lambda d by small d. That is equation 2. The distance between two consecutive bright fringes is xn minus xn n minus 1. You will get, after simplifying, lambda d by small d. Therefore, width of the dark fringe, which is in between two consecutive bright fringes, is given by lambda d by small d. So therefore, equation 4 gives width of a dark fringe. Similarly, second condition, case 2, condition for di. Di means destructive interference. So put delta is equal to 2n minus 1 into lambda by 2. Therefore, x will be equal to d by d into 2n minus 1 into lambda by 2. And x dash will be d by d into 2 into n minus 1 into lambda by 2. So x dash is the distance of the n minus 1 dark fringe on the screen. X is distance of the nth dark fringe on the screen. Take the difference, you will get the width of bright fringe, which is also equal to lambda d by small d. Therefore, beta bright is same as beta dark, which is equal to lambda d by small d. So equation 6 gives you fringe width in biprism experiment. Fringe width of the interference fringes in a biprism experiment. And here, since capital D is not known to us, to find beta, we can use this formula. Deviation produced by a thin prism, you know that it is given by D is equal to n minus 1 into A. This you have studied at PU level. Deviation produced by a thin prism is n minus 1 into A, where A is the angle of the prism, n is Ri of the prism for a particular color. This formula holds good only for refraction through thin prisms. So now let us continue with this. If capital D, small d and beta are known, wavelength lambda can be calculated. So angle of deviation theta will be equal to alpha into n minus 1, where n is Ri of the prism. Now in figure 1, that is triangle S2ES, tan theta is d by 2 by A, or d by 2 is A tan theta, that is A into theta, because theta is small, tan theta can be done as theta. That is equation 7. Substituting the value of theta in equation 7, we get d by 2 is equal to A into, in place of theta, you write alpha into n minus 1. So D is equal to 2a alpha into n minus 1. Now put capital D is equal to a plus b and substitute in equation 8. We get, that is from this equation, put capital D is equal to a plus b and then substitute for small d from equation 8. We get beta is equal to a plus b into lambda divided by 2a alpha into n minus 1. So this formula you can make use of to find fringe width in a biprism experiment, because you cannot measure small d, even you cannot measure capital D. So in the equation, earlier equation, that is equation 6, we have replaced capital D by a plus b and small d by this equation 8. So equation 9 gives you fringe width formula in a biprism experiment, interference by division of wavefront in a biprism experiment. Next, let us discuss about next heading, determination of wavelength of monochromatic light using biprism. Now look at this figure first. This is the optical bench. It's a flat metallic support with leveling screws at the bottom, and its length is about 2 meters, and there are mounts to keep the optical devices, which are known as mounts. In the first mount, you have a vertical slit attached. In the second mount, the biprism is fixed as shown in the figure, such that its principal section is a triangle and refracting edge is facing the slit. And in the third mount, L denotes a convex lens. In the fourth mount, you have an eyepiece fitted with a screw. You can focus for the images, focus for the interference fringes by adjusting the screw. So this is a arrangement using biprism. You need an optical bench and 4 mounts are required. In the first mount, you will have an arrow slit whose width can be adjusted by a screw that is not shown in the figure. The slit is vertical and the slit width can be made narrow as possible by using an adjusting screw. In the second mount, you have a biprism mounted such that its refracting edge is vertical and it is facing the narrow slit. And in the third mount, you can place a convex lens whenever it is required. Provision is made. Initially, the lens is not mounted, but later on, when you are doing the experiment, the lens, convex lens L, is placed in the third mount. And in the fourth mount, a telescopic part along with the eyepiece is fixed. You can adjust the focusing screw. You can see the well-defined interference fringes through the eyepiece, and you can measure even fringe width. And leveling screws are provided at the bottom in order to level the optical bench. Now let us see what are the adjustments. Initial adjustments or preliminary adjustments. The first one is optical bench is leveled with the help of spirit level and leveling screws. So you should adjust all the leveling screws with the help of a spirit level. You can make the optical bench horizontal. That is called leveling. Second adjustment, the slit, biprism and eyepiece are adjusted to the same height. So all the three, the narrow slit, yes, biprism mounted on the mount, and also the eyepiece, all the three should be adjusted to the same height so that the light from the slit will pass through the biprism and reaches the eyepiece. And you can view the interference fringes through the eyepiece, other side of the eyepiece. Therefore, the second adjustment is very important. And the third adjustment is the eyepiece is focused on its cross wires. There are 2 cross wires in the eyepiece. One of the cross wire must be made vertical, the other one will be horizontal. The vertical cross wire is a reference to take the readings. And the fourth adjustment is The slit is made narrow and vertical and is illuminated by the monochromatic light, that is sodium vapor lamp of wavelength lambda, which is to be determined. And the fifth adjustment is the biprism is mounted such that its refracting edge is vertical and parallel to the slit. And the sixth adjustment is the slit is made narrow, biprism is rotated till the fringes become sharp. So once you see the fringes through the eyepiece of the apparatus, then you can find fringe width by difference method as shown in the tabular column. Look at the tabular column. This is fringe number. You can start from 0. The one fringe number, the one which you have focusing the vertical crosswire with the fringe, you just call it as 0th fringe. Take the reading of the micrometer screw provided in the eyepiece. That reading, let it be X. Next, take for alternate fringes 2, 4, 6, 8, 10, 12, 14, 16, 18. So these readings, let us call it as X, and the other readings, let us call it as Y. If you take X difference Y, it may be Y minus X or X minus Y. It will give you a width of 10 fringes because 10 minus 0 is 10, 12 minus 2 is 10, 14 minus 4 is 10. Similarly, 18 minus 8 is also 10. So therefore, this last column, X difference Y, gives you width of 10 fringes. Therefore, fringe width beta is, you take the average value of X difference Y, this mean value, divide by 10, will give you the fringe width beta in meters. And then distance between the slit and the eyepiece, capital D, can be directly measured with the help of a scale on the optical bench. Even a scale will be fixed on the optical bench. Directly you can record the distance between the eyepiece and the plane of the slit from the optical bench, that is capital D. Next, measurement of small d. Small d is distance between the two virtual coherent sources, S1 and S2, that cannot be directly measured because virtual images cannot be caught on a screen. Now, this is a procedure to find small d. A convex lens L of focal length f, which is less than capital D by 4. Remember, capital D is distance of the eyepiece from the plane of the slit. Suppose if it is 80 centimeter, divide by 4 means 20 centimeter. You should use a convex lens whose focal length is less than D by 4. It is mounted between the biprism and the eyepiece, and the lens position is adjusted to L1 to obtain sharp magnified images of S1 and S2 are obtained in the field of view of the eyepiece. That means you will get the images of S1 and S2 in magnified form on the screen. Now the distance between these two images is measured as D1. That is D1. So therefore, magnification M1 is V by U, image distance or object distance. It is equal to D1 by D. Similarly, without disturbing the position of the prism and the eyepiece, the convex lens L is moved to position L2 towards the eyepiece to get sharp diminished images of S1, S2. Now the distance between the two images is measured as D2 in the second case. So in this case, magnification M2 will be D2 by D. So if you multiply from 1 and 2, M1 into M2 is V by U into U by V, which is equal to D1 by D into D2 by D, which is equal to D1 D2 by D square. It is equal to 1. Therefore, D square is D1 D2. Therefore, D is square root of D1 D2. So using equation 3, we can find what is small d. So thus d is calculated using equation 3, and then the wavelength of light lambda is calculated using the formula lambda is equal to beta is known, capital D is measured, small d is measured. So using equation 4, we can determine the wavelength of light. So to measure D1 and D2, you can look at this figure. So here at position L1 position of the lens, U is the object distance, V is the image distance, magnification is V by U. It is equal to D1, D1 by small d. And in the second position, L2, you will get diminished image. The two images will come closer to each other. Measure this distance D2. Then D means distance between S1 and S2. D is given by square root of D1, D2. So this is about experiment with biprism. So let me stop at this stage. I will continue the remaining portion in the next class. Thank you.